Greetings, welcome to another iCampSA video. So today we are doing an exemplar paper for your June examination. So let's start from question 2. So here they're saying a car of mass 1500 kg needs to maintain a constant speed of 10 meters per second up a constant hill of height 4.56 meters, inclined at 0.46 to the horizontal. Okay, so now they're saying here the coefficient of kinetic friction between the surface of the hill and the tires of the car is 0.017, this one here, right? Okay, now they're asking us to define the term power as applied in physics. Okay, so now when you're doing power, I always urge people to use your exam guidelines. Okay, what is power? Power is the rate at which work is done. Okay, rate at which work is done. That is power. Okay, right, that should be fine. Then they're asking us here to draw a labeled free body diagram to show all the forces acting on the car while it moves up the incline with a constant speed of 10 meters per second. So for 2.2, so that means we're going to consider a car maybe at any point, maybe here, maybe the car is here. Okay, maybe the car is here. Right, that's what we're going to consider. Right, so that means when we are dealing with an inclined plane, we can do something like so. This is your free body here. First force that we can start with is the normal force. The normal force is always perpendicular to the surface. Okay, and then we're going to have maybe the force of the engine. Okay, this is the force that is pulling the car up. So here we said this is the normal force. Maybe this is the force of the engine or the applied force to keep the car going up, right? And then we're going to have another force here, which is our frictional force. Okay, so far we've got 3 forces. So usually you're advised to use your marks here to guide you. So 4 marks means 4 forces. Okay, then the last force that we haven't added here is your gravitational force or your weight, which is going down like so. This is going to be your Fg, then this is going to be your Fk. Okay, then you've got your free marks just like that. Okay, now let's see what the second question, the other question is asking from us. Now they're saying here, show that the magnitude of the kinetic frictional force that acts on the car is 249.98 newtons while it moves up the hill. Okay, so here they've already given us what we call your coefficient of friction. This is your 2.3. So now with the coefficient of friction, we know that the frictional force here is equals to the mu k, which is your coefficient of kinetic friction, times the normal force. Okay, and we know that your mu k, they said it was 0.017. Okay, according to the statement here, this one. Okay, and then now that means we just need to calculate what we need to calculate your normal force. But now in this case, when you have an inclined plane, your normal force is not going to be equals to your Fg. So your normal force is not going to be equals to your Fg, but rather it's going to be equals to the component of Fg. So when you have something like so here, you're going to have here your component here. This is going to be your Fg perpendicular. Then here, this is going to be your Fg parallel. This is your Fg parallel. This is what you have. So then now you need to be able to calculate this. What do you use when you are calculating these components? Okay, So if you put your angle here, you've got FG and you are looking for F perpendicular. So that means I've got FG, so I can say cos theta is equals to, what am I looking for? I'm looking for your F perpendicular, and then over hypotenuse side is going to be FG. So this one will work for us, right? Remember your components of weight, how you calculate them. So in this case, that means your normal force is going to be your Fg cos theta. Okay, this is just simply cross multiplying here, because Fg perpendicular is equal to Fg cos theta. That's how we get to that, right? So now once you are here, you can easily then come back and say your Fk is equals to mu k, and then instead of n, you're going to say Fg cos theta. Okay, but now we should also note that we have Fg as mg. Fg is equals to mass of the object times the gravitational acceleration. Okay, gravitational acceleration is what? Your 9.8 meters per second squared. Right. So now we can come back here and say 0.017 all times my Fg is going to be the mass of the car is 1,500 kgs times 9.8, and then all of this is going to be cos 0.46 degrees. Okay, this is what you have, right? So if you punch your calculator, then it should give you your answer. Okay, and then from my calculator, I'm getting 249.89, like so. Okay, newtons, which is very much close to what you were given here. Okay, so just make sure you punch your calculator very well. This is what you've got. Okay, now the last question of this question 2, that's asking us here to use the Work-Energy Theorem to calculate the average power the engine of the car must provide to ensure that the car is able to get up the hill from A to B whilst maintaining this constant speed of 10 meters per second. Okay, so we are going to 2.4 now. 2.4. Okay, first things first, you must know what is the Work-Energy Theorem. Okay, what does it mean? So the Work-Energy Theorem is the one that says your work done is equal to the change in, or the net work done is equal to the change in kinetic energy. Okay, that's the first step. You need to know this. So once you know this, then it's easier for you. Okay, then you can deal with whatever that you need to deal with. Okay, so now let's get to it. So from here, what I can do, if I want to calculate this work net here, I can say this is the change in momentum in kinetic energy, which is 1/2 m. Then I can say Vf squared minus Vi squared. Okay, so from this here, we are saying the velocity is going to remain constant in between these 2 points. This is what they said here, whilst maintaining this speed, right? So if it maintains the same speed, so that means here the net is going to be 0, because you're going to have your 1,500 here, and then for your V is going to be 10, the final at B, and then the A at A also is going to be 10, like so. And then that means this is going to be 0. So now your work net is 0. Okay, joules. This is what you have, but it doesn't end here. What you need to do then is you need to do work done, because the work done by each of these forces. Okay, so in theory, we are going to say maybe the work done by FA, which is the engine, plus the work done by your frictional force, plus the work done by your FG parallel, okay, plus your FG parallel, like all these other forces, right? But now the work done by normal force is going to be 0 because it's perpendicular to the movement. Also, the work done by the FG perpendicular is also going to be 0, so we cannot account for that. Okay, right. And then you're going to have 0 here. All right, this is what you've got. So now let's then find out what happens, because this is the work net. So in what was going to happen, this was going to be just equals to delta E K, which is your kinetic energy. But we know that this is 0, right? And then we can then go and find out our forces. We know that work done by a force is equals to, so let's just say work is equals to the force itself, the displacement, then cos theta. Okay, but now if we go back and then we check here, we can see that we've only got this vertical height here, and then we've got the angle. We don't have the distance it moves in an incline. So that means we can come back here and then try to get that height, that distance here. That means it's going to be our displacement. So this is, if we are looking here, this is going to form a right angle triangle. Okay, then if we've got this y here, we've got the angle, and then we are looking for h here, which is our delta x. We are going to use sine. So if I just write it here, I can say sine theta, which is 0.46, is equals to my 0 is 4.56 over hypotenuse side, which is what I'm looking for, right? So then that means the hypotenuse side is going to be 4.56 over sine 0.46, like so. Okay, this is just roughly here. So we can come back and write it here so that we've got the displacement that we're looking for. So I was saying, we're going to say, let's put it here. Let's say sine 0.46 is equals to your 4.46 over your hypotenuse side. Okay, is it 46? Let's check. 56 actually. Sorry. So this is supposed to be 56. Right. So that means your hypotenuse side is going to be 4.56 over sine 0.46. So now we need to know what is this. Let's punch our calculator and see. So from my calculator, I'm getting 567.98 meters. Okay, this is the displacement, which is your delta x, right? So now that means then you can come back here and then substitute what you are looking for. That means what you're gonna have is the force of the engine, which is your FA. It's going to be displacement cos theta. Let's just cos theta plus, then we've got FK displacement again cos theta plus your FG parallel, then displacement cos theta again. Okay, and then all of this is equals to 0. This is what I've got. So you can add the other forces so that it's much easier for you, or it's easy to follow. Okay, so now that we are here, we can then start playing around with the numbers that we already know. Okay, so we don't know this force here applied by this truck here, or the engine. So this is going to be FA. We're just going to take it as is, and then substitute 567.98, then cos. Now, yes, well, this is where the question lies. because now we are dealing with an inclined surface, right? So this is the inclined surface, this is the car here, right? And then this is the force. So now the angle that you're considering here is going to be the angle between this surface and this force. Okay, so in this instance it's going to be 0, right? You're not going to regard this one here. Don't use this one, because now we are speaking about this angle that we're speaking of here. If you look at this formula, this theta is actually the angle between your displacement and your force. Okay, please keep note of that. So then it means we've got this 0 here, then plus your FK. We calculated our FK here as 249.89. So it's either you can use this one or you can use this one here that they gave you already, but it's closer, so it shouldn't be an issue. So 249.89, and then you've got your displacement here again, which is going to be 567.98, right? And then now cos theta. Now let me just not put this cos as yet. So now when we're dealing with now friction, so again we've got our car here, but now this force is going this direction, whereas the displacement is this side. This is going to be a displacement. So now that means the angle between this displacement and this FK here is from here to here. Okay, that means this is going to be 180 degrees. Okay, this is what is going to happen. So that means for your FK, you're going to have cos 180 degrees. Okay, that's what happens. That means then the same thing, you should expect the same thing for FG parallel, right? But now let's be careful again around FG parallel. Let me just do it in a different color so that you see. So this is going to be plus your FG parallel. Remember the components. You said that your FG perpendicular was cos, right? It was FG cos theta, right? That means your FG parallel is going to be FG sine theta. Now this theta that we're talking about here is different from this theta that we're talking about in the work done. Okay, this one is from the inclined plane, which is your 0.446. That's what makes it different here. Okay, so that means you're going to have this force first, which is going to be your mg 1500 times 9.8. This is your mg. Okay, and then we're gonna have sine 0.46. This is now our force. All of this is our force. And then we're going to then go get the displacement. For the displacement, we have 567.98. This is our displacement. And then after getting the displacement, we then go and get what? We then can get our cos now. So we're going to add our cos. So this is going to be cos. Again, with regards to this, we're going to have something like so. Your perpendicular one was like so. And then we said that your parallel one is like this. And we can see that this is moving down. It's moving opposite to what? This is going to be FG parallel. This is moving opposite to the movement of this car. So that means even again, we've got your displacement that sits here. So what's going to happen here is then again, you've got your angle as your 180. So that means even here you're going to have 180, and all of this is equals to 0. So now we can be able to get this force here. We can't be able to calculate this force here, right? Because we've got all the other stuff known. The only thing that is unknown to us is this force. So we can just press our calculator and get the force. Okay, so here this is 0. So that means what we're going to end up with in this instance here is we are going to have 5, 6, 7.98 FA or F engine or whatever you can call it, then plus. Then from here onwards, we can punch our calculator and see what we get. Let me punch it. Okay, so this is what I've got for my question. Okay, for my calculator. So here, then we're going to say again, we have this 567.98 FA equals to, we're just gonna bring it this side, 932.52 plus 67,031 and then 80, like so. Then it's gonna allow us to divide it. So I'm gonna come back now, punch my calculator and see what's the final answer. And this is what my calculator has given me. Okay, now from here I can then come here and see if I can be able to calculate my power, because we were looking for power all along. Okay, so now we can say power is equals to the force times velocity. This is one of the formulas we use for power. Okay, so it means we're going to say 367.91 then times what is our velocity. Our velocity is going to be 10 meters per second. Okay, so then our power is going to be, let's punch our calculator once again. Okay, so therefore from my calculator I'm getting 3,679.1. This is going to be what? Okay, this is our power here. So this is it for this question. We're going to move to the next question. Okay, so now we are looking at question 3. So here they're saying during a fire extinguishing operation, a helicopter remains stationary or hovers above a dam while filling a bucket with water. The bucket has a mass of 80 kgs and is filled with 1,600 kg of water. It is lifted vertically upwards through the height of 20 meters by a cable at a constant speed of 2 meters per second. Right. The tension in the cable is 17,000 newtons. Assume they are not sideways motion during the lift. A friction is not ignored. A friction is not ignored. Okay. So first question is state the work-energy theorem. Right. Work-energy theorem. We run and we visit our example line again. Then we're gonna say the net or total work done is equals to the change. Actually, the object's change. The object's change in kinetic energy. Okay, so this one, find a way to put it in simple ways, but now follow the example lines. We're saying here the net or total work done is equals to the change in the object's kinetic energy. Okay, it's equals to the change in the object's kinetic energy. objects in there is equal to the change in the objects kinetic energy. Okay, so this means what? This means the same thing we were saying before. We said W is equal to the change in kinetic energy, like so. EK, actually, not K. EK. We had something like so. Okay, so if you just remember that W is equal to the change in EK, you know that you've got your work-energy theorem. Now say they're saying, draw a labeled free body diagram showing all the forces acting on the bucket of water while it's being lifted upwards. So now we are looking for the bucket of water, which is going to be 3.2. Okay, bucket of water. So now let's start. We've got here our dot. One thing we should note is that we're going to have this tension of 17,000 going up. So that's the first thing. Okay, this is the T, which is your 17,000. Okay, and then now what we're going to have is the weight. Okay, which is the FG. But now they've said something, air friction is not ignored. This is what they're saying here. Air friction is not ignored. So we might as well add it here. Okay, this is going to be air friction. So it's up to you how you call it. I'm just going to put it as FK. But this is air friction. Okay, right. So then the next question here, they're saying use the work-energy theorem to calculate the work done by air friction on the bucket of water after moving through the height of 20. So after moving 20, right? So that means here we've already got our delta x. So now instead of it being delta x, what's going to happen is going to be delta y, because now we're doing with the vertical movement. X meant we are dealing with the horizontal movement. Okay, remember for work what we had before was W, the force here, delta x cos theta. This was the horizontal movement, right? So let me just say horizontal. This was horizontal movement, but now we are going up and down. So that means we're going to say F delta y cos theta. Okay, this is a vertical movement. This is what you have. So nothing much changes, it's just for context. Okay, now we know that our work done, we said our work done is equal to the change in kinetic energy of the object. Okay, so now what should we note here? So now they said here this thing will be moving up at a constant speed of 2. So if we've got a constant speed, okay, we said if we have a constant speed, it means this change in kinetic energy is not actually going to be anything, it's going to be 0. So let's say you've got something like this. I'm going to write it again. So what you have here is your W 1 over 2m and then Vf squared minus Vi squared. So if they're saying constant, it means it's not changing. So that means it's going to be 2 squared minus 2 squared. Then this is going to be 0. Okay, this is your work net or total work. So now that you've got total work as 0, so what we need to do then now is that you already have your free body diagram there. Let me just redo it for you. So you have your free body diagram, you have your T here, you have your A here, FK, and then you have your FG here. Okay, so that means we have 3 forces. So what we can do is we can say we have work done by T plus work done by Fk, or we can say Fa and then by So let me just say Fk is equal to Fa, which is your air friction, as a side note. So then we have Wfg equals to 0. This is what you have. Okay, then we can start working on this. For T, we're going to have T delta y cos theta. Then plus your Fk, we were looking for work done by this Fk or Fa. So we're just going to keep it as is. Fk. Then plus, then here we're going to have mg, which is your Fg, right? And then cos. This is your Fg, then x, then cos theta. All is equal to 0. Okay, then from this we can then do our stuff. So let's go and check this out. So we know that this is 17,000, T is 17,000, and then they said our y here is 20 meters. This is what they said. They said it's somewhere here. It's 20 meters. After moving through a height of 20 meters. Okay, so it means we're just going to come here and say this is 20, and then cos. So what is happening is you've got this free body diagram, you've got your displacement here, or you've got your displacement here. Okay, this is your change in y. So the angle between this t and the y is 0. So it's going to be 0. Then plus Wfk. Then plus for mg, we're going to have the mass of the bucket. The mass of the bucket at the moment was, before being filled, was 80 kg. Okay, then we fill it with water, and then we have 1,600, like so. So that means the total now of the water and the bucket is going to be 1,680. That's what you're going to have, 1,680. So here it's going to be 1,680 times 9.8. This is our force. Then this is going to be 20. But now you can see that this displacement is here, but the Fg is on the opposite side. So that means the angle is going to be 180. So that means this is going to be cos 180, like so. All is equal to 0. Right? So we can then simplify this and say, and let's punch our calculator instead. Okay, and this is what I'm getting from punching the calculator. Right? Then I can subtract this stuff again. 1, 2, 3. And then I'm getting Wfk is equals to minus 10,720. Okay, joules. This is what I've got here as my final answer. Okay, right. I think that's it for this question here. Let's see if we've got more questions. Okay, now we are looking at Doppler effect. Question 4. So it's saying here a traffic official is stationary. We're just going to mark the important notes on the side of the road where the speed limit is set to 100 kilometers per hour. He hears a hooter of a car traveling at a constant velocity on this road. Okay, the hooter emits the sound waves of frequency 433 hertz. Okay, the wavelength of the sound detected by the traffic official is 0.72. Then they're saying here the speed of sound is 340 meters per second. Okay, now let's state Doppler effect. So I'm going to write it down and then come back read it for you. Okay, Doppler effect here, we're talking about the change in frequency of sound detected by the listener, because the sound and the listener have different velocities, right? That's how you first look at it. then relative to the medium of sound propagation. I think it makes it easier when you look at it in this manner, right? Okay, let's see what are they saying in the next question. So here they're saying calculate the frequency of the waves detected by the traffic official. This is your 4.2. So frequency of the wave. So let's say here they say the wavelength of the sound detected by the traffic official is 0.72 meters. This is the wavelength that we have. So what we need to say is V is equal to your frequency times your wavelength here. This is your wavelength, okay, which is already given to us. So we've got the frequency of sound, which is the velocity of sound, which is 340. So that means here we're going to say 340 meters per second. The frequency that we're looking for, then 0.72 here. Okay, then your frequency is then going to be, let's punch our calculator and see what do we get here. So the frequency that I'm getting is 472.22 hertz. Okay, this is the frequency that is detected by the traffic official, right? And then you can see that the hooter emits this. Okay, this is the waves, the frequency of the wave that is emitted by the hooter. But now the traffic official is detecting 472. Okay, now is the car traveling towards or away from the officer? So this has just been answered by what I was saying right now. Okay, so 4.3. So what's going to happen here is that this is moving towards the officer. The car is moving towards the officer. And why is that? It's because the officer is detecting a higher frequency compared to what this hooter is emitting. That is your reasoning here. Okay, if we had lesser frequency that is detected by the traffic official, it would mean that the car is moving away or the hooter is moving away. Okay, so the reason here is the detected frequency is higher. Detected frequency is higher than what the source is emitting. Is higher than the frequency from the source of the source. Let's just say that. Okay, this is your reason. In simple terms, then you can use also these frequencies, these two frequencies. It's this one here and this one that we just got. Okay, now let's see. They're asking us here to perform a calculation to determine whether the car is exceeding the speed limit. So that means we need to find out what is the velocity of the car. And then we can know if the car is exceeding the speed limit or not. Okay, so this is your 4.4. So to calculate that, we're going to need our FL is equals to F plus minus velocity of the listener over V plus minus velocity of the source, then Fs. Okay, we have F. Now we said it's moving towards. That's what we said about a car. Then this is going to help us determine what our formula is going to be like. So here, first of all, VL is 0 because it is said that the traffic official is stationary. Okay, so now after that we can then go save FL is equal to V over V plus minus VS Fs. So we now need to update this plus minus. So if it's moving towards and the frequency is increasing, that means I need to have a minus. Okay, that's what I need. So here I'm going to have a minus. I'm not going to have a plus because I'm trying to decrease my denominator so that the frequency can increase. So you don't divide this coefficient because this is a coefficient, right? Okay, now we can then go and get all the frequencies. So the frequency of the listener here that is observed by the listener is 472.22. So I can say 472.22 equals to the velocity of sound is 340. So that means here I can say 340 over 340 minus Vs is what I don't know at the moment. We are looking for that. And then Fs is going to be 433.64. 433.64. This is what we have here. Okay, and then we can play around with this, and then we get what is our velocity. Okay, now this is a matter of maths. When you are here, you can divide both sides by this number here, so that you can divide, you can be able to cross multiply. So I can come here and say this is divided by 433.64, even here 433.64, so that this goes away. Okay, so now I'm left with this. Let me see what I'm getting. So from here I'm getting 1.089. I can put it like so. Then I have 340 minus Vs. So now when I'm here, I can then cross multiply, right? I can cross multiply and say 1.089 times 340 minus Vs equals to 340. This is what I have. Let me apply the math. So my calculator is giving me 27.79 meters per second. Okay, but now we must note that it doesn't end here. So now we need to convert these meters here, then convert them into kilometers. So you can say, come here, Vs is equal to 27.79 times 3.6. This is your conversion here. Okay, so now let's see if we multiply by this, what happens. So 27.79 times 3.6. I'm getting 100,044 kilometers per hour. Okay, and now this is above 100. Okay, so I can say the car is exceeding here. It exceeds the speed limit. Okay, this is this question. So now they're asking us, if the car travels at a lower constant velocity, how will this affect the frequency detected by the traffic official? Is it greater than, less than, or the same? Think about it. Okay, so I can come back here and say FL again, Vs, V minus Vs, okay, and then Fs. Okay, now still I'm comparing this frequency that is going to be detected, I'm comparing it to this frequency. So if we decrease this velocity here, which is our Vs, that means we are still going to have a smaller denominator here. So that means you're dividing it lesser. So it's more like you have an apple and you want to share it amongst 5 friends or 2 friends. Who's gonna get more apples between these two groups? So that means the 2 people are gonna have larger portions compared to the smaller ones. Okay, so even here, that means what will happen here is we're gonna have still a greater. Okay, we're gonna have a greater than frequency. It's gonna be greater than this Fs. Okay, maybe, and then if you are comparing it to what already exists or what we've already calculated here, if you're comparing it to this previous answer that we did, then it would be at least slightly less. Okay, not even, it won't be the same because you've reduced the velocity. Okay, but now if you're comparing it to the source, it's gonna be a bit more. It's still gonna be more because of the formula that I just wrote here. Okay, That's what we're talking about. Okay, coolies. That is for the that is it for the first part of this preparatory exam question. Let's meet on another part. Thank you.